Hello everyone, this is Katisha. In this video, I'm going to go through the electricity end of topic test higher tier for physics combined science. Question number 1. A correctly wired plug and cable connects a washing machine to the mains electricity supply. The washing machine has a metal case. A fault causes the live wire to make an electrical connection with the metal case of the washing machine. The earth wire is not connected to the metal case of the washing machine. Explain why it would not be safe for a person to touch the metal case. Now, because it's a metal case, it will conduct electricity, right? And because it's not connected to the earth wire, if you touch the metal case, the current will actually pass through you, resulting in the person actually getting electrocuted. So how do we write this? The person could get an electric shock, you could say, so the person could be electrocuted, right? Because there is a current in the person. So these are the two key points, right? Because you're trying to explain why the person will get an electric shock or they will be electrocuted because there's a current in the person or there's a current passing through the person. Second question, a student investigated how the current in a filament lamp varied with the potential difference across the filament lamp. The diagram below shows part of the circuit used. So you have a variable resistor here, a filament lamp and a battery. The graph shows some of the results, so it's only this part of the graph is showing just the top part. So you can see the potential difference is the x-axis and the current is in the y-axis, and as the potential difference increases, the current is also increasing. Write down the equation which links current, potential difference and resistance. Part A, write the equation which links current, potential difference and resistance. So this is the equation V equals I R, which is potential difference equals the current multiplied by the resistance. You can write it as a symbol equation or word equation. Part B, determine the resistance of the filament lamp. So resistance of the filament lamp when the potential difference is 1 volt. Now, using the above equation, V equals IR, right? Potential difference is 1, and they are asking for the resistance. Now I need to know the current, which I'm going to find it from the graph. So what is the current when the potential difference is 1? So when the potential difference is 1, it's over here, right? So it's this first point, and it's on the 8th box. Right? There's 10 boxes between here and 0.1. So if I divide 0.1 by 10, I'll get 0.01. So each box is 0.01 amps. So 8 of those boxes is 0.08. The common mistake would be students not reading that and simply writing the answer as 0.8 rather than 0.08. So rearranging the equation, divide both sides by 0.08. Resistance is 1 over 0.08. So that's 1 divided by 0.08 gives me 25 over 2, which is 12.5. 12.5 ohms. The photograph below shows an LED torch. The torch contains one LED, one switch, and 3 cells. Which diagram shows the correct circuit for the torch? So you have the batteries on the top. You can see this battery connection. This is actually wrong because it has to be positive to negative, and then positive to negative, and then here it's a negative again. So that's incorrect in there. And For the second one, the battery is connected correctly. Now the direction of the current is from positive to negative, so the current is actually going in this direction. Now if the current is going in this direction, the LED will not let the current go through in this direction, which means there's a mistake here, which leaves number 3 as the correct option, because the current will actually go from positive towards negative. When the switch is closed, it will go in this direction. That triangle is indicating it will allow the current to go pass through this. So that's means C is the correct answer. 3.2, write the equation that links charge, flow, current, and time. So Q equals IT is the equation. Q for charge, I for the current, and T for the time. The torch worked for 14,400 seconds before the cells need replacing. The current is 50 milliamps. Now milli amps a thousandth, or milli is 10 to the power minus 3. So I need to convert this to 50 milliamps to amps first of all. So 50 divided by 1000 would be 0.05 amps. The common mistake would be students not converting that correctly. So the charge is I times T, and the current is 0.05 multiplied by, now you don't really need to convert the time, it has to be in seconds. So 0.05 times 14,400 gives me 720. Write the equation that links current, potential difference, and power. So again, using the equation sheet, P equals IV or VI. Power is equal to the current multiplied by the potential difference. A light bulb has a power input of 40 watts. So that's my power. The mains potential difference is 230 volts. That's my potential difference. Calculate the current, which is I. So rewriting the equation, P equals IV. 40 watt equals the current multiplied by 230. In order to find the current, you need to get rid of this 230. So you divide both sides by 230. So 40 divided by 230 equals the current. So let's do that. 40 divided by 230 is 4 over 23, which is 0.1739. So I can round that off to 0.17, or 3 decimal places or significant figures, 174. Question 5.1. The student investigated how the resistance of a piece of wire varies with its length. The diagram below shows the circuit used. So you have again a variable resistor, battery, the ammeter, and a voltmeter connected across the wire. Explain why the student needs to adjust the variable resistor each time she changes the length of the wire. Now, when you change the length of the wire, the resistance is going to change. That's what we're trying to investigate. Now, you want to keep the current the same as possible. Reason, if the current is actually too high, the wire is going to get hot, which can affect your readings. So here's the answer. The variable resistor changes the resistance of the circuit, and in order to keep the current the same, so the temperature of the wire is kept constant. right? And there's another another reason why you switch it on and off in between readings is also to keep the wire temperature constant. The student recorded 3 measurements of the potential difference across a 0.1 meter length of wire. Calculate the value of X. So these 3 values added, including X 0.18 and 0.15, the mean of these 3 values is 0.17. So in order to find the total, you could multiply this 0.17 by 3. So 0.17 multiplied by 3 gives me 0.51. 0.51. Now these two values added up. 0.18 plus 0.15 gives me 0.33. 0.33. So if I take away 0.33 from 0.51, that should give me the answer. That's 0.51. Wait, sorry. That. So 0.51 minus 0.33. 0.18. So that's actually 33 0.18. 0.18. Next question. The graph shows the results of 5 different lengths of the wire. Describe the relationship between the length of wire and the resistance of the wire. Now, as you can see, as the length increases, the resistance also increases. It's linear because it's a straight line. It's positive correlation, and it's directly proportional. Reason being, when I increase the length from 0.1 to 0.2, the resistance is actually doubling. So it's going from 0.8 to 1.8 to 3.2 of 3.4 here. So resistance is directly proportional to the length. That actually gives you both those marks. If you simply say as length increases, resistance increases, you're just going to get 1 mark. Or if you say it's a positive correlation, you get another mark as well. A student builds a circuit. The circuit is shown below. So you have in this circuit a cell, a light dependent resistor. This would be the common mistake that most students make, identifying what this component is. It's a light dependent resistor, and a voltmeter is connected parallelly to it, and a fixed resistor and the ammeter, which is connected in series. Explain how, so which means you have to give reason. It explains how the readings on both these meters change. And how will the reading on the ammeter and the voltmeter actually change when the environmental conditions actually change? So imagine you can get 3 marks for describing what happens to the ammeter reading and the voltmeter reading. Now, the ammeter measures the current in the circuit. Because it's a series circuit, the current is same throughout. So that's the ammeter is going to measure the current. Right? And that current, the current in that circuit depends on the resistance of the circuit. So here you have resistance 1, and this component also has resistance 2. So the total resistance can affect the current. If the total resistance increases, then the current will actually go down, because remember, the total resistance is, you simply add up the resistors. So if the total resistance increases, current will go down. If the total resistance goes down, because it's a fixed resistor, if the resistance here goes down, total resistance will go down, which means the current is going to go up. Now, what happens in an LDR? Well, it's light dependent resistor, which means when light hits it, it allows a current to go through this component. The more the intensity of light, the more brighter the light is, the more current will actually go through, which reason the resistance actually goes down. If the resistance goes down, what happens to the voltmeter reading? Now, the potential difference here from the power supply is actually shared between this fixed resistor and this LDR. So if the resistance goes down, current increases. So if the light intensity increases, resistance will go down, the current will increase. That means the potential difference across this will also increase. Because the potential difference across this is increasing, right? Now remember, the total potential difference from the power supply has to be shared between these two components. Right? How do I explain all of this that I have gone through to get 6 marks? Resistance of LDR changes when light intensity changes. When light intensity increases, the resistance of LDR decreases. So the overall resistance of the circuit decreases. Potential difference across the total resistance remains unchanged. So we're talking about the potential difference across the total resistance remains unchanged from between both those components, which means the current in the ammeter increases. There's less resistance, so the current in the ammeter increases. Now the potential difference across the fixed resistor increases, and the potential difference across the LDR decreases. Right? Reading on the voltmeter decreases. Potential difference is shared between the components in series. The lower the resistance of the LDR, the smaller the share of the potential difference. Reading in the voltmeter decreases. Hopefully that makes sense. This is a challenging question for 6 marks. Right? Spend some time reading through the bullet points and understanding what is happening in each stage. Right. Question number 7. The graph below shows a current potential difference for a filament lamp. Explain how the resistance of a filament lamp. So they're asking about the resistance. Here they have the graph is talking about potential difference and current. So you need to interpret it in terms of resistance of a filament lamp changes as the potential difference across it increases. Now, when the potential difference is increasing, you need to think, why is the current actually increasing? That means because there's less resistance. But when you increase the potential difference, the current is actually going down and it's becoming stable. What's happening is the resistance is slowly increasing up to a maximum, and then it stays the same, which causes the current to lower down. So meaning not current to lower down, to current to decrease. So here the current increases when the potential difference increases, which causes the temperature of the filament to increase. So the resistance increases, right? You can't simply write do not accept resistance increases and then levels of, and you need to say that the resistance increases. Question number 8. The current from an electric shock causes a person's muscles to contract. The person cannot let go of the electric circuit if the current is too high. The graph below shows how the maximum current at which a person can let go depends on the frequency of the power supply. So you can see the maximum current at which a person can let go at 10 Hertz is about 12.5 milliamps. Now you want the current to be lowest at which a person can let go, which is at the bottom of the graph, because current is what actually hurts people. So the lowest current at which a person can let go is found at 50 Hertz. The UK mains frequency is 50 Hertz. Explain why it would be safer if the frequency was not 50 Hertz. I think that's a mistake here. It should why it would be safer if the UK mains frequency was 50 Hertz. And there's an error in the question because here's the marking scheme answer. 50 Hertz has the lowest maximum let go current. A higher, lower, or a different frequency would allow people to let go at a greater current. So you want the current to be as low as possible. Question number 9. A hybrid car has an electric motor and a petrol engine. The electric motor in the car is powered by a battery. To charge the battery, the car is plugged to the mains power supply of 230 volts. That's my potential difference. The power, which is P, used to charge the battery is 6.9 kilowatts. Calculate the current. Now 6.9 kilowatts needs to be changed to watts. So for that you would multiply that by 100. So let's multiply that by, sorry, not 100, 1000. So that's 6,900 watts. So the equation P equals IV. Power is 6,900 multiplied by the current. Oops, sorry, made a mistake there. Power equals the current multiplied by 230. So in order to find out the current, rearrange the equation. 6,900 divided by 230 should give us the answer. So 6,900 divided by 230 gives me 30 amps. Question number 10. A student built a circuit using filament lamps. The diagram below shows the circuit with two identical filament lamps. So this is a parallel circuit. Compare the currents I1, I2 and I3. So I1 is the total current. And when it comes to a junction, it's going to split up. Because it's identical filament lamps, it will split up equally because the resistance of the lamp should be equal. So you can write this answer as an equation, and you can write any of these 2 points to get those 2 marks. So I1 equals I2 plus I3, or and I2 equals I3. The first two bullet points would get you the 2 marks for this question. That brings us to the end of the questions in the higher tier paper, and I'm going to go through the questions from the foundation paper now. Question number 1 from the foundation paper questions. The photograph shows a toaster. The toaster is connected to the mains supply using a 3-core cable. Tick one box from each list to complete the sentences. The insulation around the earth wire is green and yellow. The insulation around the wire, live wire, is brown in color. The insulation around the neutral wire should be blue. The diagram below shows a circuit. In which position should or could a switch be placed so that both lamps can be switched on or off at the same time? J and L will only switch off this first lamp. K will switch off the second lamp. M controls the current to both the lamps. So the current goes from through the ammeter, splits up in the junction, joins up. So if you break the circuit there with a switch, then that will stop the current going through the circuit. So that's M. Figure 1 shows a lift inside a building. Figure 2 shows part of the circuit that operates the lift motor. The lift can be operated using either of the 2 switches. Explain why. The main reason being this is a parallel circuit here. So closing any of them will actually complete the circuit. The switches are in parallel, so closing either switch completes the circuit. The graph below shows how the current through a filament lamp changes after the lamp is switched on. The normal current through the filament lamp is 1.5 amps. Why might the filament inside a lamp melt when the lamp is switched on? So the normal current is going to be somewhere here, which is what you get after about 0.075 or 0.08 seconds. At the start, between the first 2.5, 0.025 seconds, it's actually spiking up to 3.5. So the reason why might the filament lamp inside a lamp melt when the lamp is first switched on? The current goes higher than the normal value, right? Or the current goes higher than 1.5, which is too high, and it will melt the filament. A student investigated how the resistance of a wire varies with the length of the resistor. A student investigated how the resistance of a wire varies with the length of the wire. The diagram shows the circuit used. Which variable is the independent variable? That's what you're actually changing. That would be the length of the wire being tested. The variable which is dependent variable is your investigating the resistance of the wire. A student took repeat readings of potential difference for a 30 centimeter length of the wire. Complete or calculate the mean potential difference. So how do you calculate the mean? You add all three of these values and divide it by 3. So divide that by 3 and that will give you 0.16. The length of the wire was increased to 60 centimeters. The current in the wire was 0.5 amps. The mean potential difference across the wire was 0.32. Calculate the resistance of the 60 centimeter. They have given you the equation resistance equals potential difference. That's my potential difference, which is 0.32. 2 divided by the current, which is this 0.5, and that gives me 0.64 ohms. Now, this 60 centimeter value, we are not actually using it as part of the calculation. A student below built the circuit shown in the diagram below. So I have a series circuit of 2 fixed resistors. Calculate the total resistance in the circuit. The resistance is potential difference divided by the current. So the potential difference is this 12 volts. That's my potential difference, and that's my current. So 12 divided by 1.6. So 12 divided by 1.6 is 7.5 ohms. 7.5 ohms. Calculate the resistance of P. Sorry, the resistance of P is 3.5 ohms according to the diagram here. Calculate the resistance of Q. So the total resistance is 7.5. You take away 3.5, and that gives me 3.5 again. 3.5. Figure 1 shows a mobile phone being recharged with a portable power source. A student needs a new power source. Figure 2 shows 3 different sized power sources. So you have the compact, large, and the high capacity. The table gives data about the 3 different power sources. The compact, number of charges is 1, weighs 100 grams, has mass of 100 grams. Large, 5 charges, mass of 200. High capacity, number of charges 10, has a mass of 600. The student chose the large power source, so they are choosing this. Suggest why the student chose the large power source. Now, there's 2 ways of comparing it, writing down the answer. First is compare the first 2. Why would you choose the large compared to the compact? Well, the mass is only double, but the number of charges has increased by 5 times. So large is better compared to the compact. Why choose the large compared to the high capacity one? Well, the number of charges is actually doubling, but the mass is 3 times more. And you can talk in terms of the number of charges to the mass ratio as well. So let me show you the first answer. So here, comparison with the compact power, source is 5 times as many charge, but only twice the mass. And comparing it with the high power source, although half the number of charges, it's only 1/3 of the mass, or you can say the reverse. Another way of writing down the answer was to calculate the charge to mass ratio. So if I divide the number of charges by the mass, so 1 divided by I can find the mass per gram divided by the charge. So 100 grams per charge. So that's, let's write this down. So mass compared to the charge. So 100 to 1. So the ratio is 100 to 1. Here it's 200 divided by 5. That's 40 grams per charge. That's 100 grams per charge. 100 grams per charge. And if I divide 600 by 10, that's 60 grams per charge. So ideally, the second one is the best. So here's a different way of writing down the answer, comparing either the charge per gram, or you can describe it in terms of number of grams per charge. Question number 8. The mains electricity supply has an alternating potential difference. Which diagram shows an alternating potential difference? If it's alternating or AC current, it has to go from the positive to the negative. So that's the positive to the negative, right? As you can see, B and C are both on the positive side, so the alternating is A. Question number 9. The diagram shows how the national grid connects power stations to consumers. Label the parts of the national grid K, L, and M. K is step up transformer. L will be the power cables, or just cables, not wires. We have to refer it as cables, or you can describe them as power lines. M is step down transformer. That, I believe, brings us to the end of the question. The rest of the questions in the foundation paper are similar to that in the higher paper, which is from the question 1 and so on. So you can refer back to the top front of the video for the answers for these questions. Thank you for watching, and that brings us to the end of the video. I will see you in the next video.